So let's continue with our discussion on series and parallel. Okay, series and parallel. Now, I want to highlight this part, if you are ready. Now, Mr. Che has already designed the lab, so I looked at it. It looks like fun. So we're gonna probably implement it once Mr. Che prints everything. Most likely next week. Most likely next week we're gonna take 1 hour to play around with the components. I'll see what components I can find in the lab. Then we can try it out. But the main idea is this. I want you to be very observant in the setup of the electric circuit. Now, two main objectives. For this chapter, two main objectives. One is you must learn how to draw. You must draw. Very simple, like what I've been drawing on the board. Right? You must remember what the components represent, how to place them in the circuit, and how to draw. Okay, that's the main idea. Can? First thing. Second thing, of course, is our mantra. You must remember when something changes, what happens to the rest of the qualities, like the voltage, the resistance, the current, all these things. Okay, Ken? So these are two main big picture concepts you must remember for this topic. Clear so far? Clear so far? Now, let's try something now on your notes, okay? Since you're a bit tired, then I will do a bit of work. Now, very simple. I will give you this very simple thing. I want you all to draw a circuit in your on some space around your slides, right? I want you to draw a circuit, okay, with a few things. First of all, I want you to draw a circuit that is series with 3 bulbs, okay, 3 cells, okay, 1 resistor, 1 switch, fixed. Good question. Okay, 3 bulbs, 3 cells, 1 resistor, 1 switch, and 1 ammeter. First, now in series. No need to label, but it's good to put it for your own notes. So remember, okay, later we'll check. Okay, so everybody now on your any blank space available, you don't have to draw very big, but any blank space available, I want you to draw a series circuit with these 3 bulbs, 3 cells, 1 resistor, fixed, 1 switch, and 1 ammeter. Now, I've drawn this a few times already. I just want you all to practice. Switch, open first. Open first. Think about what is series. Series, we talk about series is, not this one. The previous slide, series means what? The component is one after another. One after another. Okay, thinking. Okay. Next time don't say tai hai, say I'm thinking. Yes, you can draw on your full sketch, it's okay. You can draw on the slides, it's okay. Just draw somewhere. Later, Mr. Che and I will walk around to check. See whether you understand. This is to understand. Try. Everybody try. Because this is expected behavior you must show. Expected. Now, once you're done, very simple. Once you're done, I want you then to draw a parallel circuit with the same setup. I mean, not same setup, same number of components. Parallel circuit. We say already, right? Series circuit means the components are all one after the other. Parallel circuit means there are branches in the circuit. Up to you. You can draw anywhere you want first. Don't worry. Slowly. Don't forget the ammeter. How to draw resistor. Look back at your notes. It's inside. It's okay. You can ask your friends. Learn. Where's the stuff? Everybody must try, please. thank you, Reiko, for using a ruler. I really appreciate that. Thank you. Free hand. Come on, guys. Everybody try. Okay or not? Oh, okay. Okay, your bar a bit small, but okay, good. See you this one? Series or parallel? Very good. Try. Then now you draw parallel. Since you've done the series, you draw parallel. Open, yes, open. It's okay. Up to you. You draw it up for me first. Don't worry. I just want you to draw practice. You're done already? This one is what? You don't know? What is this circuit? Very good. Correct. It's correct. All in series are one after another. Now you try parallel. Which one? Don't care. It's okay. Okay, this one looks parallel. Yes, very good. Okay, good. Okay. Okay. Looks. Hey, where's the switch? Don't forget. Where's mine? Relax. Okay. You're missing something. Where's your resistor? Okay. See, I need to do this. Okay, now. Okay. Listen. Okay. Okay. Very good. You have all the components. Okay, now. I'm coming. Once you're done with the series and parallel, I want you to add in, okay, a voltmeter to measure voltage across one bulb. Okay, add in a voltmeter to measure how you will use to measure voltage across one bulb. Okay, Ken? You done? Yes. That means I want to measure the voltage across one bulb. Remember, voltage is like a drop in energy across one component. You remember? Any bulb. Just pick one bulb. Yeah? Like this. Very good. Very good. Excellent. Very good. Okay, how? Coming, Annie. Yes. Good. This one. Correct. You forgot something. You forgot ammeter. Ammeter is the circle at the A one. Yours? Writing. Okay. Yes. Ben? Very good. Excellent. Very good. Okay. This one very messy. Your switch, but it's okay. Excellent, Ken. Very good. Okay, Ken. All good. Okay, looks good. Where's your voltmeter for this one? Okay. Switch, ammeter. You're drawing your voltmeter. Try. This one's Salah, wrong. You look at his. Theirs is correct. Yours wrong. Voltmeter must be in series or parallel. Hey, where's the parallel circuit? Drawing. Okay. It's okay. I know you are. I can see the confused look on your face. It's okay. Calm down. Most important is, do you remember which are the different components? Okay. Yep. Betty. One is a cell. This is correct. This is true. Wrong shape. Though there is like that, but it must be like this. Not like this. You see a difference? Yeah. Yes, there's the switch. You can draw either, but I open it again. Yeah. No, voltmeter is across a component, so it's here. This, yeah. So, but this is correct setup. So this is series of barrel. Very good, because they're all one up. Okay, you okay? You got the basics. Don't panic. Don't panic. Whenever there's something, don't panic first. All right. Okay. Good. Okay. Very good. Okay. Excellent. Okay. Now, It looks like most of you got the basics of the drawing. I just want to say a few things about the drawing, okay? In general. Listen. Number one, I really appreciate, for example, sorry, I borrow yours. Now, if you take a look at Reiko's drawing, right? She is very neat. Okay, she uses a ruler to draw the wires. Now, listen up. This is my expectation for the class. Whenever you draw wires, thanks Reiko. Whenever you draw wires, I know on the board I'm very lazy, so I apologize. I am the one who caused you all to be so lazy, right? But in actual fact, when you draw wires, you need to draw them so that they are always straight and then they have corners. This is what I mean. For example, right, let me draw this very quick series circuit for most of y'all. Most of y'all will have drawn something like this. 3-cell battery. Now, when you draw a circuit, when you draw a wire, right, it must always be straight lines, and try to use a ruler to do it. But of course, if you can still sketch it, it's fine. So for example, if you want to draw open switch, right, it must be always straight lines. And then you can add in a resistor here, right? And then you can add in a bulb, 1, 2, 3, right? 3 bulbs. Yeah, I'll be saying it, no ruler. And then after that, what else I said? Ammeter. Is that it? That's all. Okay. Okay. Now, let me give you some words of advice. Very quickly, where to put the different components. Now, listen up. In any circuit, if you want to put in the ammeter to measure the current, the best place to put it is near the battery. Okay? That means you should put the ammeter near the battery. Either this side or this side doesn't make a difference. It's the same. But it's good to put in near the battery to measure the current of the whole circuit. Now here's something I want to share with you guys, and you guys can find this out during the experiment. Okay? Now, if each battery is 1.5 volts, what is the total volt of this battery? 4.5, right? Now, if you put a voltmeter to measure the voltage across the battery, for example, if you put a voltmeter like this, what will you see on the voltmeter?
4.5.
Very good. You should see 4.5. 4.5,
If they ask us to put 3 cell, right, then we put one positive, right, connecting to each other. Then the other one correct again.
Something like what I said before, right? So Benjamin is asking, what if we do something like this?
It is still correct,
Like that? Of course, you put it like that, it is still correct, as in this is
3 cell.
still 3 cell. Yes. Because the question never say must be 4.5 volt. So technically you are still correct lah. But don't draw it like that lah.
So isn't it 4.5?
You can argue the examiner lah, but I will recommend all of you be conventional a bit lah.
So like that 1.5.
Don't be so picky lah. Like that lah. Okay. Now, here's something that I want you to remember. Okay, listen. Listen, very important. Okay, listen. In a series circuit, okay, and this is you will find out during the experiment, the voltage across all these things, that means if let's say you take a voltmeter, you measure the voltage across this resistor, plus the voltage across this first bulb, plus the voltage across this second bulb, plus the voltage across this third bulb, what do you think will be the total voltage? Okay, I take the voltmeter. I measure the voltage across the battery is 4.5 volt, correct? if I take the same voltmeter and measure the voltage across the different components, the resistor, the bulb, if I add them all up, they should add up to 4.5 volts. That means the voltage 1 plus voltage 2 plus voltage 3 plus voltage 4, voltage 1 plus voltage 2 plus voltage 3 plus voltage 4 equals to 4.5. Most weak. Sorry. Oh no. Don't have. Anywhere else can. Now listen. Why is it like this? Do you remember my slope analogy? Do you remember? Don't remember? Do you remember my slope analogy? I said this, right? I said that the battery is like a slope. If let's say this battery is 4.5 volt, it's like a slope with 4.5 meter height. Okay? And every time the current passes through one component, it's like dropping a little bit. Do you remember that? Do you remember what I said? So imagine, let's say, hello. Imagine the current is moving from here. Let's say I connect the switch. Right? Connect the switch. So the current is moving here. It goes through past the first resistor. When it goes past the first resistor, it will drop a bit. So imagine like this. This is the slope. So if the current is moving like this, moving like this, right? Once it reaches the first resistor, so I say this is the resistor, it will drop a bit. After that, it travels a bit more. When it passes through the first light bulb, you'll drop a bit again. I didn't say that but it can be the same Yeah. So that means, listen, ladies and gentlemen, this is the important part. Every time the current passes through one component, it will lose some energy. So that's the concept you must have. Every time the current, okay, I write down for you here. When current pass through a component, it loses some energy. Okay? And this loss of energy can be seen as the potential difference, the drop in the slope. Okay? So therefore, if this is the maximum, so-called the slope, because 4.5, let's say 4.5 volt is the how high the slope. After the current move here, this is considered what? Back to zero already. That means, like, for example, if I draw something like this, this is the first resistor, second resistor, third bulb, fourth bulb. By the time, so this is the first resistor, right? This is the first light bulb, second light bulb, third light bulb. By the time the electricity, the current pass through all these things, it should come back to here, because it's like the thing travel, the current travel like that, past the first resistor, drop a bit. Then move past the first light bulb, drop a bit. Second light bulb, drop a bit. The last light bulb, will drop to the ground already.
So, but drop to the ground, then go back, then nothing left.
So go back lor.
Then no more good.
Then go again. So it's like roller coaster. Okay, think of it as a roller coaster. You all see roller coaster before? Imagine the battery is the part of the roller coaster that go up. It's like, so you imagine this thing going up like that. Then after that, drop. So imagine this part is the flat ground. Once there's a component, they drop a bit. They go down to the lamp, drop some more. Every time you pass a component, you drop. Until you drop to the bottom, then you go up again. Can you understand? Can you imagine not? How roller coaster better? Okay. Okay, so listen, hello. So Kurt is asking, what if the bulbs are the same, meaning same resistance? It means that the drop is the same. Okay? The drop is the same. If the bulbs are different resistance, then the drop is different. Now, question. If the bulb is high resistance, do you think the drop is more or less? If the resistance is high, if the bulb, let's say this bulb resistance is high, the drop, which is the voltage, should be high or low? Do you remember our mantra?
High voltage, high current low.
Very good, correct. So if the resistance of this bulb is high, it means that the voltage across this bulb is high. Means that the drop is more. You know, I'm trying my best. I'm thinking of all sorts of analogies to help you understand. Yes, must always remember the mantra. It applies to everything. Okay, so far okay. Wow, half an hour to go this. Okay, can Huh? The what? Lie down. Okay. Can
So you can
Yeah, very hot. I'm very excited. I jump here, run here. Yes. The what? Current. Say again, friend. The current. Oh, current. That means the resistance high, voltage will be high, then the slope will be more. Okay. Any questions? Okay, huh? Okay. Very nice, okay, good. So, if all else fails, just remember the roller coaster. Use it to help you understand. Okay, can I now talk about, this is series circuit, series circuit. I talk about parallel circuit. Can I erase can? Wait. Take picture? Yes, please go. Yeah, I do a lot of, because I mainly teach bio. No, I click this on in. Relax. Don't panic. Huh? My what? My what? Yeah. No. He's swanning me. He said I only have 12 subscribers. It's okay. Yeah. I'm not like the the PSY or people. Got like how many subscribers? 10,000. Trying the 10,000 subscribers. Yen you. Okay. Got her singing.
Yes.
Oh. The what? What? Okay.
Last one.
Then must subscribe, huh?
Last one.
Plus. Okay. Alright. Why you laugh when you fall off your chair? Okay. Alright. Okay. Can I erase this? Alright. Okay, can? Yeah. Okay, now listen, Okay, I think parallel circuit will give it a miss first. I'll come back with visit. Yeah. Okay, this one okay? Can I continue? Okay. Okay, next one, Okay, so you have this picture, right? Okay, so all you need to do is remember this. Remember this, Resistor in series, light bulb less bright. Resistor in parallel, light bulb brighter. We'll try this in the lab. Okay, I'm not gonna focus on this too much because this one is so crucial. Okay, now, this part, be easier because this part is basically just understanding the example only. That's all. Okay, so class, there are only three main effects. Three main effects of electricity you need to remember. All you need to do is remember the example. I will describe a little bit how it actually works, but some of them are very cheap, I also don't understand. So I will just share with you what I understand, and we just need to remember the effect and the example. Is that okay? Okay, ma? Can I? Alright. Okay, so only three effects. Heating, magnetic, and chemical. That's it, three effects. They will ask you example. Example only lah. Alright. Okay, so now heating effect is the easiest. Heating effect is the easiest because the concept is very similar to what you guys experience. It's similar in idea to friction. Friction, right? So friction, you know, will always produce heat, right? Heat and sound and light. Even if it's hot enough, you produce light. So friction will always produce heat. And it's the same concept. If you imagine electrons to be like, I don't know, marbles or tennis ball or soccer ball or whatever. Tennis balls. Okay lah. Okay, or whatever it is. And imagine if, let's say, a lot of these are flowing past a narrow, whatever, a path or something, it will always generate friction. Because they will bounce across against one another, they will rub against one another and things like that. So, this one, easy. Any questions about electric current producing heat?
No.
No questions, Simple. Okay. Next one. Okay. Applications of heating effect, very standard one. Almost everything around us, a lot of this are heat generated, generates heat like our electric iron, ovens, everything, okay? Even light bulbs, they generate heat first before it generates light. The reason why it generates light is just that because it heat up so much that it glows, that's all. Okay, so light energy is still come from heat energy. Any questions? Can I? This one very standard, okay? You all just need to write in the, copy in the microphone. Nichrome lah, microphone, hello? Your microphone generate heat
Fast enough.
Maybe can. Oh, that one later, that one. But that one is not electricity. Yeah lah, friction produce heat, yes. Oh, you what happened? Yeah lah, understand. Okay? Can I think I'm losing you already. I'm sorry. Okay. Again? Can I? Bear with me for a while. Now, this one is the most cheap one. This is the one I don't understand. I also don't understand. but I have to still tell you lah. Now,
Then don't test it.
no lah, still have to test lah. Okay, now listen. Hello. Now, even though this is very hard to understand, but this discovery has a very large impact on our lives. I'll tell you what. Now, somehow, I don't know, maybe we can show this. Do we have? We can try to use the iron powder. Yeah. You can pass the current and then use the iron powder to show the field, the magnetic field. Okay, now, listen. Hey, hello, you're like X-Men. You like Magneto, yeah, Magneto. Listen. Okay, hello. Excuse me. Alright. Now this discovery is quite... Okay, listen. Run out paper. It's okay. Okay, can I? Now, this is an effect that I don't know how to explain, but it just happens, and I don't understand why. So the idea is this. I'm trying. The idea is this. When electric current flows through the wire, somehow it will always generate a magnetic field. Yeah. As long as electricity flows through a wire. That is why, right? I don't know whether you guys have ever seen like electricians when they come to your house. If let's say they want to find buried cables, they use a sensor. They can track where the cable is because it generates an electric field, a magnetic field. Slowly. Okay, now. So. Hang on. Slowly. So the idea is that when electricity is passing through a wire, it will generate electric field. And people have so-called amplified this to make something called electromagnets. You know electromagnets? Now, all the motors that we know, electric motors, every single one of them runs on electric magnets, like our fan. Anybody open up a fan before? What do you know? What is inside? Okay, yeah. Okay. If you open up a motor, any of the electric motors, right, you'll find that inside the motor there are two cylinders, and one of the cylinder has a lot of wrapped wires. That is the electromagnet. It's a very strong electromagnet. But the other piece is a magnet. So you always have two pieces. One is electromagnet, one is a magnet. For the car is a combustion engine. I'm talking about electric motors. Cars also electric motors. So all the fans, everything that runs electricity has electromagnet. Okay, so you just have to remember that electricity creates a magnetic field, and when you wrap the wires around an iron bar or iron, it becomes magnet. Okay? So when you switch on the current, the electromagnet has magnetism, it's magnetic, but you switch off the current, then don't have. So that's the idea. Okay, I think there'll be one slide that talks about users. Correct? Yeah, users at the back. Yeah, so it's okay. You missed something. Okay, let me here. I have it. When electric current passes through a wire, the compass needle is also. What is that? Can't remember. Okay. Right, you may ask your friends to help. Fill in the blanks here. Yeah. This is the top left slide. Guys, would you want to have a copy of this slide? like, I know it printed for you, but do you want this with all the answers in the blank? Okay, I put it on the portal for you also, okay? Okay. Question. Can I? You copy this one? Last part? This part? Oh, still copying, okay. Cannot. Go home ah? Asking go home ah? Huh? Got test ah? Oh. Hey, you all got test later ah? Oh, okay. Very fierce eh? Job please.
Look at the date.
Oh. So it's today ah? Huh? You say you go McDonald's order Happy Meal ah? Hey, I want this one, I don't want this one, I want that one, I just want this. Who's your lovely teacher? Small teacher?
Mrs. Chan.
Who's Vivian Chan? Neck very long.
Pick up when
I wonder what you all talk about me when I'm not here.
very handsome.
Yeah. Okay. Hello. Yoo-hoo. Okay. Can we come back? Okay, we finish up, huh? Okay. So some examples. This one is what, huh?
Vacuum.
This one.
Clean.
Crane with the electromagnet to pick up the recycled metal of iron. This one.
Vacuum.
Okay. Can Okay, wait. But before I say can you write this. You better write. Because some picture not very good. Okay. Because if let's say the question is give an example of how you use electromagnet, you must write lah. So I'm gonna write. You write down inside. Right. Electromagnets are used to separate. I'm trying to see what's the easiest way to phrase it. Separate iron from scrap metal. Okay? Can separate iron because iron is magnetic, so can be attracted by magnets. No, it's not. Okay. So you're right. Malcolm is right. Scrap. S-C-A-P. Sorry. Scrap. Yeah. Okay, Malcolm is correct now. Iron is just one of the few metals that are magnetic. That means can be attracted by magnet. But there are a few others like nickel and cobalt, right? Nickel and cobalt, right? Okay? These are also two other metals that are magnetic, that means can be attracted. So for example, the new Singapore coins. The new Singapore coins have a lot of nickel. So they are magnetic. Yeah. Can. Okay. Yeah. Alright. Okay, can. Alright. Yeah. Hey. Must be you that man. Okay.
The four magnetic silver iron nickel.
Huh? Cannot. Can I? Yeah. The new Singapore coins have very high amounts of nickel, so they're magnetic. Okay. Hey, what are they on? What my slide there? Oh, because of here. Okay, never mind. I'll skip that one. Okay. 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 Don't flirt lah, don't flirt. Okay. I think I lost you already.
Never lost me.
I haven't lost you. Thanks. I haven't lost Ernest. I lost, I think, half the class. Okay. Lost means you're not paying attention. You're like drink out already.
Or you teach me.
I know. 15 lah, 15. Okay. Okay, let's okay. Can we, how about this? Guys, we finish up chemical effect, then we do a bit of workbook, then we take a break. And Ken? We finish this one first, then we take a break. Alright. Okay, come. Stay with me. Okay now.
Just start it.
Oh, yeah. They call the potato clock now. Lemon. Water. Like, there's a clock. You can power the clock there. Yeah. You must take it to something right. Okay. Don't Okay. Alright. Are you okay? Okay, continue. Okay now? Yeah, I know. Are you always like that? No, right? Only my class. No, also not true. I'm so sorry. You know, I know you don't like because I also don't like, and I find it very hard to. But I'm trying my best. Okay. Cannot. What's the problem? Okay. Cannot. Okay, now listen. Now, this one actually this topic, even though it's very hard to understand, there are many applications. Like just now, Reiko was telling me in a primary school. Have you ever seen this lemon battery or potato clock, that kind of thing? Watermelon, yeah, all sorts of. Okay, now. Okay. Listen. Now, how? Okay. I would ask Mr. Che, right? When one of these days we go to his workshop, we go and saw open a battery.
I don't mind. You want a battery?
Because, okay, now listen, no, not saw open your phone. Now listen, this effect is actually one of the most important discoveries that enable us to have portable electronic devices. Because without understanding this effect, we can never have batteries. And without battery, we cannot power our phones, our whatever, like I cannot power this. Right?
Our power bank like
Yes, exactly. Now, all the like for example, all the power banks that you use, you buy. Slowly. That is the thing. That's the thing. Now, all the batteries that we have, for example, your dry cell. Dry cell is like your. Have you ever opened a dry cell before? Like Duracell, Eveready.
Yeah, Eveready.
Have you opened it in half or chop it in half? You don't know Eveready? Oh, no, got generation gap. My time got ever ready battery. Energizer. Okay. The ever ready never. It's the one with the black cap one. No lah. Now listen. One of these days, right? I will try. Maybe we can. I can ask Mr. Che to saw open a battery. Saw like that. Can not? You try lah. You help me try. Saw like that. Not like that. Like that. No, like that. Like that. It's like this the battery, right? Like that. Okay, I ask Mr. Che to cut. Now.
You only burst when
Huh? Okay. That one can. Now listen. Hello. You. Hi. Now listen. I die already lah. Bola. In front of me 什么 Scold me Okay, listen. Okay. Yeah, I know you are very restless. Assuming you do jumping jack. Yeah. Okay. Can I finish up with this? And now. I asked Mr. Che to cut a dry cell because the dry cell does not contain acid, but it contains something called electrolyte. Huh? Something like that. But it's now for the dry cell, right? Now, what an electrolyte is just that an electrolyte has a lot of ions inside, dissolved, like same as a sports drink. But for dry cells, the electrolytes come in a paste form. Paste, not liquid. That's why it's called dry cell. But for all your rechargeable batteries, I can tell this, all your rechargeable batteries, almost 99% of them are made with acid. That's why I don't want Mr. Che to cut open the thing. It's quite dangerous. All have acid one. Alright, quite dangerous. And the acid is quite strong. Now, just now, Clement asked, how do you actually, when you charge a battery, what actually happens? Yeah. From red to green. Yeah. Now, the idea is this. The reason, okay, let me explain very quickly and as simply as I can how something like this can generate electricity. Now, those of you who have seen the potato clock or the lemon clock, what happens is this: you stick two different metal. Okay lah, not interested lah. Strange, I don't know why you're not interested. I thought interesting. Huh? Cannot. You know cannot. Don't ask me things I cannot give you. Cannot.
Can you just say
Okay, no, I can't. Okay. 5 minutes. Okay lah, I stare at you, you stare at me. I will touch you. I can't do anything. No, I can't. What? Huh? What? Next time? Yeah, ask. Yeah, go. What question? It's inside the battery in the form of chemicals. Okay, think of this. when you use the battery, use the energy is inside the chemical compound, chemicals. The chemical change from one thing to another thing, and that gives you the energy. When you charge it back, you convert from the other thing back to the original thing. So it's like a conversion. Acid and different metals. That's it. It's inside, it's just chemicals. You can see. The square box, rectangular box with an arrow on top, like that. And an arrow. This must be an arrowhead. Okay. Yeah. Okay, hey guys, please, I put my assignment there. I put already. So please have it done by Friday, right? Is it Friday? Because I think I won't see you Wednesday, Thursday, right? I only see you Friday, I think. So please do as much as you can. Last year. So can you try to do as much as you can? Okay. Actually, very hard, isn't it? Okay. Huh? No, cannot. No, cannot give up. No lah, it's not HSD or whatever. Cannot. Must try. Must keep trying.
Try and try. No, you can fail. Which topic is very good?
All bio topics. Chemistry still okay. It's a lot of writing. Okay, thank you, class. Okay. Very hard there.